Hello, my name is Ryan St. Clair. My research project is on a spectral investigation of well-known partial differential equations discretized by finite differences. I've done this under the direction of Dr. Ozcan Ozer for the Department of Mathematics. This research project is an applied mathematics research project that may be used in developing technologies such as piezoelectric devices. These are layered, smart materials that generate electric potential in response to applied stress, and vice versa. They're being developed for use in a variety of technologies, including the ones pictured, like biomedical devices, robotics, and other industrial uses. In order to be able to harvest energy from vibrations in these materials, or to generate appropriate reactions from an applied current, we must be able to characterize the vibrations along a beam of the piezoelectric material. In this case, longitudinal vibrations along the device are described by the wave equation. The wave equation does not describe bending or compressional waves, but only longitudinal vibrations. So the wave equation describes vibrations along a string of length L. My research is focused on characterizing the eigenvalues of the wave equation under two different boundary conditions. Here, we show mixed Dirichlet and Neumann boundary conditions. This means that the left end of the string at x equals 0 is at a fixed position. We can view this as being clamped or attached to a wall. The right end of the string is free. The other boundary condition that we will consider is a pure Neumann condition, in which the string is described as free or loose at both ends. I'd like to mention that Sidney New, a previous student of Dr. Oz, described the wave equation under a third boundary condition, pure Dirichlet condition, for her senior seminar in 2018. So why discretize? Well, we desire to be able to determine and control vibrations along the string/beam using a finite dimensional sensor placed at a single point, placed at the tip x equals L of the string. The partial differential equations that I showed you describe the wave continuously. However, we will approach the wave equation through the discrete finite differences approximation. We do this because sensors functionally operate in finite dimensions, whereas partial differential equations, like the wave equation, are infinite dimensional. So we must develop the math to describe waves in a way that the sensor can interpret and then properly direct the controller to act. However, creating discretized models using these well-known approximations may have some undesired consequences, such as causing the eigenvalues for the semi-discretized case to diverge from those of the continuous case. This may lead to the discretized case losing the observability of the vibrational structure that is shown by the continuous case. So my research spatially discretized the wave equation using finite differences. This method approximates the wave at a finite number of nodes along the length of the string. The discretization parameter h is given by the length of the string divided by the number of nodes plus 1. By discretizing the spatial portion of the wave, we obtain the following approximation for the second spatial derivative of our function. Then the wave equation can be approximated at each node by the following formula. Notice that our boundary conditions have also been approximated, such that the left-end clamped Dirichlet condition is approximated as the function at the node u0 is equal to 0, and that the functions at the node nth node un and un is equal to the node un plus 1. For the pure Neumann, or free at both ends conditions, then u0 is equal to u1 and un is equal to un plus 1. So we began by defining this eigenvector to be comprised of our functions, of our approximated functions at each node, u1 through un, and the first time derivative at each node, ut1 through utn. Then the wave equation can be written in matrix form as follows, where A sub h is an n by n matrix comprised of the coefficients of the approximated function at each node, ui1 through n. Notice that the coefficients in the first row of the first AH matrix reflect direct layer or clamped conditions, and that these will change whenever our left-hand condition is free or Neumann. We now propose the following eigenvalue problem to describe the vibrational modes of our approximated system. In examining this eigenvalue problem, we find that the eigenvector u2 is equal to our eigenvalue times the eigenvector u1, and that substituting this result, we find that our matrix AH applied to the eigenvector u1 is equal to our eigenvalue squared times u1. So now, applying this to applying the eigenvalue problem of AH to our second spatial derivative, we obtain the following equations. And in my paper, I used lemmas to prove that these following eigenvalues are true for the above equation under the mixed, clamped, and free condition and the pure Neumann free at both ends condition. Notice that these eigenvalues are finite dimensional as k ranges from 1 to n. From those lemmas, I proved the following theorems to describe the eigenvalues of the semi-discretized eigenvalue problem for the wave equation. Again, notice that these eigenvalues, the lambdas, operate in finite dimensions. And also that as the discretization parameter h goes to 0, then necessarily the number of nodes n plus 1 tends towards infinity. Now then, the gap between high frequency nodes, which is k, as k goes towards infinity, then the gap between these high frequency nodes tends towards 0. So this is important. So what have we accomplished? Well, this system was previously, as I stated, this system was previously solved under Dirac-Leigh boundary conditions by Sidney New. And that work showed that the eigenvalues for the finite difference approximated wave equation under Dirac-Leigh, or clamped at both ends, boundary conditions, diverged from the eigenvalues of the continuous case at high frequencies and as the discretization parameter tended towards 0. My research expanded these findings onto two new boundary conditions, the clamped free mixed Dirac-Leigh Neumann and the pure Neumann or free at both ends cases. As illustrated in this graphic that shows the continuous eigenvalues and the finite differences approximated eigenvalues for the mixed Dirac-Leigh Neumann condition, then we find that the finite dimensional approximations diverge from the infinite dimensional continuous case at high frequency modes. And also that the eigenvalues of the discretization model fail the gap condition. The eigenvalues of the continuous cases maintain a constant gap size, while the gap between eigenvalues of the discretized model tend towards zero as k goes to infinity and as the discretization parameter h goes to zero. This gap failure impacts the viability of this approximation as it is used in sensors, because the sensors would not be able to accurately detect high frequency modes, and in turn would not be able to generate the proper response from the controller. So this research could be continued in the future through a thorough spectral analysis of both the continuous and approximated models, especially looking at analysis of the limiting case as h goes to zero. This is important if we desire to correct the divergence of high frequency modes through filtering. The end goal is to show that the observability of vibrations along the strings is not preserved through the approximated model as it is in the continuous case. Thank you for watching my presentation.